In this module, the learning outcomes shall be to know the value of immobilizing enzymes on a solid support, to learn the various techniques used to immobilize enzymes, to identify the various common chemical reactions that are used to attach enzymes to different solid supports, and to how to evaluate the limitations of the different methods to immobilize the enzymes. Enzymes are linked to a solid and inert solid are called as immobilized enzymes. Many enzyme catalyzed reactions of industrial use are carried out on such solid matrices. Besides enabling easy recovery of the enzymes after the completion of the concerned reactions, it also enhances the useful properties of the enzymes. This module describes the various support systems used to immobilize enzymes and the chemical methods used to immobilize enzymes. Immobilization of enzymes offers a host of advantages that affords important applications in the industry, which are also described in this module. We'll first talk about the different procedures for immobilizing the enzymes. One of the first procedures will be that of covalent coupling to a polymeric matrix. In this method of enzyme coupling, functional groups on the amino acid residues on the enzyme are used to react to the matrix. The most reactive functional groups on the enzyme are the ones in its active site. These residues will preferentially react with the matrix during the reaction. In order to protect the active site, the reaction is carried out in presence of a competitive inhibitor molecule. Reactive functional groups that usually participate in such a coupling reaction include the amino groups, which can be either the N-terminal alpha amine, the epsilon amino group of lysine, or the guanidine group of arginine. The carboxylic functional group is also reactive, such as the alpha, beta and gamma carboxylic acid groupings of the C-terminal amino acid residue, aspartic acid and glutamic acid respectively. The tyrosyl hydroxyl group and the sulfhydryl group are the other reactive functional groups found in enzymes. The polymer used as a solid matrix for coupling enzymes can either be neutral, hydrophilic or lipophilic. Electrically neutral polymers that have been used to couple enzymes include nylon and acrylic polymers. Hydrophilic polymers include cellulose, dextrin, agarose, ethylene methyl cellulose and aminoethyl cellulose. Polystyrene is an example of a lipophilic polymer. Destabilization offered by linking enzymes to lipophilic polymers is more than that for hydrophilic polymers. As a first step towards coupling enzymes to various solid supports, either one or both must be activated to enable a successful reaction. The chemical reactions used to activate the polymer matrix are now discussed. One of the first reactions is acylation and alkylation. Acyl halides, anhydrides, acyl azides, isocyanates and thiocyanate, alkyl halides and aldehydes, aminocarbonates, carbonates are used to activate groups on the polymer. The amino groups on the enzymes then covalently couple to the activated matrix via a nucleophilic attack. Such an enzyme polymer coupling was used to immobilize trypsin, chymotrypsin and ribonuclease enzymes to cellulose columns. The hydroxyl groups on the cellulose were activated by reaction with bromoacetyl bromide to generate bromoacetyl cellulose, as the reaction on your screen shows. A preferable reaction used to activate cellulose is the Curtis-azide reaction, which had the added advantage of increasing the stability of the attached enzyme along with very little compromise on the activity of the immobilized enzymes. The figure shown on your screen shows you the Curtis-azide reaction. Ethylene malic anhydride is an example of a synthetic macromolecular copolymer used to acetylate the amino groups on the enzyme. The anion exchange resins such as aminoethyl cellulose are reacted with phosphine or thiophosphine to generate isocyanates and thiocyanates, which in turn react with the enzyme amino groups, enabling the immobilization of the latter. Activation of silica makes use of this enzyme reaction as well. Treatment of silica with gamma aminopropyl triethyloxysilane converts the hydroxyl groups to alkylamines, which are subsequently derivatized to isocyanate and thiocyanates as shown on your screen. Reacting an amino group carrying resins with aldehydes such as glutaraldehyde activates them by making them susceptible to nucleophilic attack by the enzyme. One drawback of this reaction is that it cross-links the enzyme and therefore the resin needs to be adequately washed before conjugating the enzyme. Beta-galactosidase enzyme is activated by this method. The figure on your screen shows you the treatment of amino group with glutaraldehyde. One other common reagent is cyanuric chloride or trichloroester-triazine, which is used to activate the hydroxyl groups on DAE cellulose resin. Lactate dehydrogenase enzyme is mobilized to such a resin. You can see the reaction of cellulose with cyanuric chloride on your screen. One of the other ways of coupling is diazonium coupling. Tyrosine residues on enzymes react with diazonium salts on a resin to generate a spacer arm between the matrix and the enzyme, which serves to reduce the steric interaction between enzyme and matrix. Higher enzyme carrier conjugation ratio is achieved by this method. The figure on your screen shows you the reaction of tyrosine with diazonium salt, creating a spacer arm. One other reaction is that of sulfhydryl exchange. Coupling of enzymes via sulfhydryl groups instead of the conventionally used amine group is also popularly done. Sulfhydryl groups can be found within a protein if there are internal cysteine residues. Cysteine residues in a protein participate in stabilizing the secondary and tertiary structure of the protein via disulfide linkages. These disulfide links must be reduced to sulfhydryls in order for them to be used for immobilization. Usually, cysteines are less in number in proteins than amino acids with amine groups in their side chains. Thus, it is possible to carry out selective immobilization by using the sulfhydryl groups than by using the amine groups. For those proteins that do not have cysteines in their sequence, a cysteine residue can be added at the end of the molecule during peptide synthesis. All the peptide molecules will now be oriented in the same way on the solid matrix. Thiolation reactions can also be used to add sulfhydryl groups to a protein. The cysteine residue in a protein is reacted with a mercaptopolymer at acidic pH for enzyme immobilization. The figure on your screen shows you the reaction of free sulfhydryl group on enzyme with a mercaptopolymer. Metal-linked enzymes. Transition metal salts can be used to make solid support for enzyme systems. These metals can be used to transform materials such as a cellulose, nylon, borosilicate glass, soda glass, filter paper and yeast cells. A solution of the metal salt is used in which the solid matrix is steeped. This is followed by filtration and washing, after which the enzyme is added. The different metal salts commonly used are titanium tetrachloride, titanium trichloride, tin tetrachloride, zinc tetrachloride, vanadium trichloride, iron dichloride and iron trichloride. The reaction on your screen shows you an example of immobilization of an enzyme using metal salts. Cross-linking. Immobilization of enzymes can also be achieved by using polyfunctional cross-linking agents. Glutaraldehyde, diazonium salt, hexamethylene diazocyanate and N,N'-ethylene bismaleimide are some of the common use cross-linking reagents. One drawback of using this method is the potential of denaturing the enzyme. The table on your screen lists the various cross-linking reagents used. Another method of immobilizing enzymes is that of adsorption on a polymeric matrix. Some enzymes are immobilized by simple condensation of the enzyme onto the surface of a matrix without any modification or activation of the functional groups on the matrix. This is called adsorption of the enzyme onto the surface of the matrix. The available surface area on the carrier becomes important in this method. Greater surface area of the matrix will allow more enzyme to bind. Charged as well as neutral materials like collagen membranes, silica gels, charcoal, clay, titania can adsorb enzymes onto their surfaces. Weak forces like hydrogen bonds and van der Waals forces, are the main intermolecular forces holding the enzyme on the matrix surface, and hence the enzyme can be washed off from the surface if harsh conditions are used, such as high temperature, extreme pH or high ionic strength. It's a non-specific method of immobilization that takes place without any selectivity, and hence there exists a finite probability of the enzyme active site being inactivated in the process. For example, in the case of the enzyme catalase adsorbed on a silica gel, there is significant enhancement in the activity of the enzyme, while an enzyme like lactate dehydrogenase is completely deactivated upon adsorption onto cellulose nitrate membranes. Another consequence of enzyme adsorption onto a solid support is the risk of stronger binding of the prosthetic group in the enzyme with the matrix as compared to the apoenzyme. For example, the heme group on hemoglobin binds preferentially to silica glass. In such a case, dissociation of the enzyme and consequent deactivation of the enzyme results. Another method of immobilizing enzyme is that of entrapment within a polymeric matrix. This method involves encasing enzymes in the internal structure of the polymer material used for making the solid support. The matrix material can be a water-soluble polymer such as polyacrylamide gels. Other naturally derived gel materials include cellulose triacetate, agar, gelatin, alginate, etc. It is also called entrapment or occlusion of the enzyme. Advantages of occlusion include control over the matrix strength, greater resistance to bacterial attack of the enzyme. Loss of the enzyme, however, must be prevented by controlling the pore size of the gel used for entrapment. Greatest attractive feature of this method is the possibility of co-immobilization of more than one enzyme. More than one enzyme can be co-immobilized at the same time. This becomes important when a series of enzyme reactions in a reaction pathway are required for a process. For example, oxaloacetate, malate dehydrogenase, citrate synthase and lactate dehydrogenase are all encased in a single polyacrylamide matrix. Since the enzymes are now in close proximity, their reaction rates increase. The rate of citrate production in such an entrapment is 3 to 4-fold higher compared to the same reactions in solution. The pathway on your screen shows you the reactions involved in the pathway for citrate synthase. Whole cells can also be immobilized by entrapping them in a gel-like matrix. For example, microorganisms, Curvalaria and Arthrobacter simplex have been encased in a polyacrylamide gel. The enzymes beta hydroxylase and dehydrogenase produced by these two organisms act upon the steroid Rextin S to convert it to prednisolone via cortisol. The disadvantage of this remains is that the enzymes in such an occlusion matrix have the possibility of leakage. Another way of entrapping enzymes is by using semi-permeable membranes to encapsulate them. The membranes used are usually nylon or cellulose nitrate and are ultra thin, with their thickness being 250 angstroms only, and the dimensions of particles made from such membranes are 10 to 100 micrometer in diameter. Such thin membranes allow free movement of small substrates but not of the enzyme. This prevents loss of enzyme through leakage. These microencapsulated enzymes are suitable to be used in vivo conditions since the semi-permeable membranes are inert and will not raise an immunological response. Liposomes are also used to encapsulate enzymes. Liposomes are microvesicles formed when lipids such as phosphatidylcholine are suspended in water. An aqueous solution of the enzyme is added and rapidly mixed with a film of these lipids that are already spread onto a surface such as glass. Spontaneous in situ formation of liposomes takes place inside. Now we'll talk about some of the properties of immobilized enzymes. The presence of a solid support offers steric hindrance to the approach of high molecular weight substrates to the immobilized enzyme. The activity of the enzyme is considerably decreased upon immobilization towards heavy substrates. The activity that is retained is assayed using low molecular weight substrates. For example, Papain, which is attached to collagen, is 50 times less reactive towards the protein casein than the amino acid derivative N-benzoyl L-arginine ethyl ester. Another example is that of trypsin, attached to dextrin, being 25-fold less reactive towards hemoglobin when compared to N-benzoyl D-L-arginine. Another factor is that of matrix environment. There occurs a shift in the pH at which the enzyme shows maximum activity once it is immobilized. For enzymes bound to polyanionic carriers such as ethylene malic anhydride, polyglutamic acid, etc., this pH shift is towards a more alkaline side. For enzymes bound to polycationic carriers such as polyornithine, the pH of maximum activity shifts towards the more acidic side. This shift in pH happens only if the buffers used are of low ionic strength. As the ionic strength increased, the pH of maximum activity shifts back towards its native value. The figure on your screen highlights the example of such a shift in pH maxima for chymotrypsin enzyme. The Michaelis constant of some enzymes also change in an ionic strength dependent manner upon immobilization. For example, at low ionic strengths, the Michaelis constant for trypsin conjugated to ethylene malic anhydride resin is 30 times lower than that of the free enzyme for the same enzyme substrate, that is for N-benzoyl D-L-arginine amide. At high ionic strengths, the Michaelis constant is more close to that of the free enzyme. These effects are due to the uneven distribution of ions in the immediate vicinity of the enzyme resin conjugate and the bulk solution. The relationship between the relative activities of hydrogen ions in the immobilized phase and the bulk solution with their relative concentrations is described by the Maxwell-Boltzmann equation shown on your screen. Here, E is the electronic charge, U is the electrostatic potential, K is a Boltzmann constant, and T is the absolute temperature. In case of a polyanionic matrix, the hydrogen ion concentration will be higher near the immobilized enzyme than in the bulk solution. That is, U is less than 0. The situation will be reverse in case of a polycationic resin. That is, U will be greater than 0. Thus, the pH of maximum enzyme activity will shift to higher and lower values. Charge species will also be partitioned in a similar way. The relative concentration of charged species with charge Z near the matrix S prime versus in bulk solution S0 is given by the expression as is shown on your screen. According to this equation, if matrix and substrates have the same sign, then S0 is greater than Si. If the matrix and substrate are oppositely charged, the substrate will be attracted towards the matrix and Si will be greater than S0. In the latter situation, there will be a saturating concentration of the substrate near the immobilized enzyme and a maximum limiting rate will be achieved at lower bulk concentration of the substrate. If we assume that the enzyme follows Michaelis-Menten kinetics, the effect of substrate concentration on the rate of the enzyme action will be estimated by combining the Michaelis-Menten equation with the above mentioned equation. This will give the expression as shown on your screen. In the equation shown on the screen, Km prime is the apparent Michaelis constant of the immobilized enzyme. Km is the Michaelis constant of the free enzyme. It can be inferred that when Ze and U are of the same sign, then Km prime is greater than Km, but if the charges are opposite, then Km prime is less than Km. The effect of the ionic strength on the apparent Michaelis constant is also predictable. If the ionic strength is represented by mu, the equation will appear as described on your screen. In this equation, Zm subscript C is the effective concentration of the charged species in the immobilized matrix. This equation gives a linear relationship between the reciprocal of the observed Michaelis constant and the ionic strength of the medium. The slope according to this linear equation is Zm subscript C divided by twice of Km, and the intercept is gamma into Km whole inverse. Now we'll talk about diffusion restriction. The kinetics of the enzyme will be a function of the technique used to immobilize it. large conformational changes in the enzyme, by virtue of it binding to the solid support, will increase its likelihood of inactivation. If the enzyme participates in a multi-site unstrained binding to the solid support, greater stabilization of the enzyme will take place. In order for an enzyme substrate to be converted into a product, the substrate must diffuse from the outer bulk solution towards the enzyme linked to the solid support. The rate of substrate conversion by the immobilized enzyme will be lower than that obtained by the free enzyme if the substrate diffusion is slower than its conversion to the product. After diffusion from the bulk solution, the substrate must be also transported inside the matrix. This diffusion rate can be made faster by rapid stirring or faster flow rate through the column. After traveling inside the matrix, both diffusion and catalysis take place together. Thus, there will be local concentration gradients of the substrate and products. Similar situation will occur in the membrane localized enzymes in vivo. For a membrane linked enzyme, the fixed law of diffusion can be applied, wherein the membrane thickness is taken as x and a zero concentration of product is assumed at the boundary according to the equation shown on your screen. Here, Fs is the local reaction rate and ds is an apparent diffusion coefficient. Substituting function of S for the Michaelis mentioned rate, we get the equation as appears on your screen. Double integration of the above equation will give the rate equation as shown. Thus, the substrate concentration required to reach half maximal rate is increased for a bound enzyme. The extent of increase is dependent on the thickness of the membrane and the rate of diffusion. At very high substrate concentrations, the effects of diffusion will be masked and the catalyzed reaction will approach its maximum rate. There exists around the membrane bound enzyme a layer called as a nursed diffusion layer of varying thickness from 10 to 100 micrometers, which is the unstirred layer. The thickness of this layer depends on the rate of stirring in the bulk diffusion. The substrate and product concentrations will necessarily be different on the two sides of this layer. The rate of the enzyme catalyzed reaction stands modified in light of this gradient of concentration of substrate and product and is related to the rate of flow of substrate towards the immobilized enzyme from the bulk solution via the equation shown on your screen. There are two extreme scenarios that can be envisaged. When the diffusion rate of the substrate is very high and exceeds the catalytic rate, that is when D subscript S is much greater than V max, then diffusion is no longer rate limiting and only the kinetics of the reaction per se contributes to the overall rate of product formation. On the other hand, when Vmax is much greater than D subscript S, then Km apparent will be much greater than Km and the reaction is diffusion controlled. Now we'll talk about some of the applications of immobilized enzymes. Immobilized enzymes can be found in more than one form. They can be found in particulate form, as column packings, as entrapped in membranes, and on the inside of tubings and on the outside of electrodes. In all these forms, enzyme activity can be easily retrieved from the reaction mixture with minimum contamination of the enzyme. The thermal and storage stability of the enzyme resin conjugates is important for this recycling. While some enzymes become more stable upon immobilization, others lose their stability upon immobilization. Two examples of the former is lactate dehydrogenase attached to DEAE cellulose and glucose oxidase immobilized on cellophane. Papain on para-aminobenzyl cellulose and glucose 6-phosphate dehydrogenase on colloidine are examples where enzyme stability is decreased. One important application of immobilized enzymes is in the industrial production of high fructose syrups. These syrups contain equal quantities of glucose and fructose. Fructose is twice as sweet as sucrose. Glucose isomerase adsorbed on DEAE cellulose and porous glass is a commonly used system to produce high fructose syrups. The reaction catalyzed here is the enzymatic conversion of D-glucose into D-fructose. Whole cells or streptomyces an organism that produces high amounts of glucose isomerase, have also been immobilized for the production of high fructose syrup. Another class of enzymes that has direct medical relevance is the galactosidases, which catalyze the conversion of lactose to D-glucose and D-galactose. This enzyme has been conjugated with cellulose acetates, titania, controlled pore glass and metal oxides. Such conjugates are then used to break down the lactose in milk into glucose and galactose. Such enzymatically treated milk is then given to individuals across the world who suffer from a condition called as lactose intolerance, in which they lack the enzyme beta-galactosidase that converts lactose to glucose and galactose. This system is also used on whey, the chief component of which is lactose, to obtain glucose in large amounts, which is then used in making artificial sweeteners. Immobilized enzyme conjugates are also used to resolve a racemic mixture. For example, the enzyme aminoacylase from the fungus Aspergillus niger adsorbed onto DEAE cellulose is highly stereospecific and is able to resolve a racemic mixture of amino acids. The chemical racemic mixture, when passed on a column, is resolved such that the L form of the amino acid is separated. L-methionine, L-alanine, L-phenylalanine, L-tryptophan and L-valine have been produced by this method. Now we'll summarize what we have gone through in this module. Immobilized enzymes have many useful industrial applications. Methods used to immobilize enzymes on solid supports include covalent coupling, adsorption onto the surface of the matrix, entrapment of the enzyme inside a water-soluble gel, inside semi-permeable membranes or inside liposomes. Using cross-linking reagents to attach the enzyme onto a solid support creates a spacer arm in between the enzyme and the matrix. Immobilizing enzymes allows reuse of the enzymes and minimum reaction time, less chance of contamination in the products, increased enzyme stability and high enzyme substrate ratio.